I'll look at 3 examples that you will find in your assignment on Chapter 2, Forces. So the first case will be a functional spinal unit. So that's considered 2 vertebrae with the disc in between there. So I guess kind of looks like this. So this is the disc that cushions the 2 vertebrae. It allows the spine to flex and extend and bend and rotate, and it will take the load of these vertebrae. Now, so these guys are vertebrae here and here. Now, this doesn't normally sit vertically like that. It's often at an angle because your spine has all kinds of curves and bends in it. So if we look at one of these functional spinal units, so this is number 1, the functional spinal unit. Look at the disc. I'll do the other vertebra here. It's often at an angle. Now, the load on top of this from your body weight is vertical because the force of gravity is always vertical. So this would be the load. And what we want to do is break this load into 2 components that act very differently on this functional unit. So one component, so we'll extend this load, the force of gravity, straight down. And the 2 components will be, once again, we make a box around the force. One component, which is called the shear component, acts to try to slide those vertebrae parallel back and forth this way. And that supplies what's called a shear force. And then the other component is the one that tends to squish the disc, and that's called the compression. So this is F, compression. And that's what would cause the disc to maybe bulge or squeeze out between those vertebrae. So the question is, how do we calculate these 2 components, the shear and the compressive components? Well, usually we're given the angle here between the functional unit and the load. And so if we translate that into our triangles, once again, here we have our triangle. The load is the hypotenuse. And then I'll do the triangle like this. I don't quite get that lined up, do I? And this is the compression. And this one is the shear. And this is a 90-degree angle. And we have, when we pull that angle into this triangle, it's here. And so you can see once again that the compressional component is the adjacent side to the angle, so it gets the cosine. So that would be F load times the cosine of that angle theta. And the shear component of the load is the sine of the angle. Okay, so that's how you handle the components of the load on a spinal functional unit. The next example, number 2, will be the bicep muscle. So let's do a really blown up. These are going to be your bones. So there's your upper arm bone, and then your forearm bone. And you guys know all the fancy names for all these bones. Doesn't really matter. It's just a fancy name. And so this is your joint. This is your elbow joint here. And the bicep muscle attaches to the bone via the tendon. So we'll draw that like this. This would be the point of insertion down here on your forearm. That's the point of origin up there at your shoulder. Okay, so now the question is, what is the direction of this force in this bicep muscle? Okay, so this is your bicep muscle. Well, remember, muscles can only pull. So they'd be pulling up on your forearm. They would also be pulling down on your shoulder. So this would be the same force. Whatever that force is, it's the same force throughout that muscle. It pulls down on your shoulder. Now, usually we're just interested in your forearm, what's going to happen to your forearm. So we're going to call this the muscle force, F muscle. Oopsie, S-C-L-E. Now, this has two components. It tends to do two things. So if we draw our X and Y axes, in this case, they'll be horizontal and perpendicular here. The muscle force, I'm going to draw this bigger over here. So this is a muscle, that's the hypotenuse. The vertical component of the muscle force points up that way, and the horizontal component points that way. Okay, the way I've drawn that force vector, that's in the second quadrant. So this perpendicular component, this is called the rotational component. So this is F rotation. And that's the part of that muscle force that causes your arm to move up like this, like you're doing a bicep curl. But this component of this muscle force, this simply pulls your forearm bone into the joint. So this parallel component here is called the compressive component, compression. And that's what's going to cause stress in this joint by pushing these two muscles together, these two bones together. Now, the ligaments, of course, there's also shear from this rotational component. It's also trying to pull this forearm up away from the joint. And that shear that's happening in here, in this joint, so shear would be happening in here. And this would be due to F rotation. Well, that's the job of your ligaments, to counteract that shear and make sure your arm doesn't fall off. Okay, so now how are we going to do these angles? Well, it depends what angle you're given. So often we're given, let's do a different one this way. Let's say we're given this angle here. And the question is, what is the rotational component and what is the compressional component of that muscle force? So if I bring it over here, there's our angle. Now our triangle looks like this. Theta. F muscle is the hypotenuse. F compression is down here. And F rotation is up here. Okay, so remember the adjacent side goes with the cosine. So the compression force, that component would be F muscle times cosine of theta. And the rotation part of that force that will cause you to do the bicep curl would be F muscle times sine theta. Okay, so pretty well every muscle force around a joint will do two things. It'll tend to squish the joint together, and then it will also tend to rotate the lower segment of your body. Okay, now the compression force, it's going to be balanced by simply bone on bone, whereas the shear force tends to be the ligaments that will keep that from slipping. Okay, the third example is a pennate muscle. And I know there's different kinds of linear and pennate and double and single and things, but I just want to look at one that kind of looks like a leaf like this. And the muscle fibers, so the tendon runs along here. So this would be the force on the tendon, which of course is then going to be attached to your bones, which are going to move your segments of your body. But the muscle fibers run this way. They're not along the tendon. Now, if it was a linear muscle, then the muscle forces would be parallel to the tendon. But in this pennate muscle, so these guys, these are the forces due to the muscle fibers, F muscle. And the angle of pennation is the angle between those muscle fiber forces and the tendon. So alpha is called the angle of pennation. And the question is, given the force due to those muscle fibers, how big is the force on the tendon, which is the thing that's going to actually make your body move? Now, if you have a really small pennation angle, And that's going to favor fast motion about your joints. But if it's a parallel fibered muscle, then you would have a much greater range of motion because you would have much more change in length if these muscle fibers are parallel to the tendon. But in this case, we want to know, so what is force on tendon given F muscle and alpha, the angle. Okay, so the muscle is the hypotenuse again, and the tendon is this component. Now, this component, I don't know what the fancy name for that horizontal component is, but this is F muscle. This is alpha, which is an angle, and this is F tendon. So once again, you're getting pretty good, I hope, at recognizing the triangle and whether to use cosine or sine. So this tendon force is the adjacent side to the angle alpha, so it's a cosine. So F tendon is equal to F muscle times the cosine of the pennation angle. Okay, so there's an example of how you get the force on a tendon for pennate muscles like your deltoids or your tibialis posterior, rectus femoris. Those are all pennate muscles. Okay, so that'll do for now.